Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the effect of temperature on the buoyancy. And this is a quite interesting topic and very good level of questions are being framed from this topic. We would discuss the questions in this video later part. But before that, let us discuss the effect of temperature on the buoyancy. So let us see that we know that buoyancy is equal to V into rho into G, where V is the volume of solid immersed in liquid and rho is the density of liquid. Okay, so this is V and rho, and we have to find out the effect of temperature on buoyancy. So let us do one thing, that let us differentiate this formula. B is equal to rho Vg, so D of buoyancy will be equal to, G is common, D of rho into V plus D of V into rho. Let us divide these two equations. So D of buoyancy upon buoyancy will be equal to D of rho upon rho plus dV upon V. Now we know that rho is equal to rho naught 1 minus gamma delta T. So by this we can say that delta rho by rho naught is equal to minus gamma of liquid delta T, because this is the density of liquid, and delta V by V we already know that it is equal to plus gamma of solid delta T, because this volume is volume of solid immersed in the liquid. So by substituting these two values in this equation, we can see that d rho by rho is minus gamma liquid delta T and dV by V is plus gamma solid delta T. So D of buoyancy, D buoyancy by original buoyancy, D buoyancy by buoyancy will be equal to delta T into gamma solid minus gamma liquid. And this gamma solid minus gamma liquid is also called as gamma effective. Okay, so D buoyancy upon buoyancy will be equal to gamma effective delta T. Now if in the first case, if gamma of solid is greater than gamma of liquid, then with the temperature, if T increases, then dB will be positive, which means that buoyancy increases. And in the second case, if gamma of solid is less than gamma of liquid, then with the increase in temperature, dB is negative. So gamma of, in fact we can say, buoyancy decreases. So this is the effect of temperature on the buoyancy, and let us also discuss quite a brilliant example to understand this concept in more depth. In this example, you can see that there is a cylindrical isotropic solid of coefficient of linear expansion alpha, and density of this cylinder is rho. This cylinder is floating in a liquid whose coefficient of volume expansion is gamma and the density of liquid is D. So it is floating partially, so you can easily assume that D is less than rho. So we have to match the correct columns. This is a brilliant example for understanding the concept of buoyancy. So let us discuss this one. So first of all, we have to check option A, that if the volume of cylinder inside the liquid remains constant, then which of the following relation is correct? We know that buoyancy buoyancy is equal to volume immersed into density of liquid into G. And in this case, the density of liquid is D, so let us write it as D into G. Okay, so in this case, you can see that if this volume remains constant, and obviously this cylinder is floating, so this buoyancy will be equal to mg, and mg is constant with the temperature. So I can say that d of vi into d, cancelling g with g, plus d of d into vi is equal to 0. What I have done, I have differentiated this equation. We have to consider that this is always floating. So if we have differentiated this equation and we see that the volume immersed always remains constant, so dvi is 0. So if it is 0, then d of d is also 0, and d of d is 0, which means that density is also constant. So density of liquid is constant. So if density of liquid is constant, then obviously gamma of liquid is 0. So the correct matching for this A option is P. Okay, now let us move on the second case, in which the volume of cylinder outside the liquid remains constant. So the volume of cylinder outside the liquid can be written as VO, and it is equal to V total minus V immersed. Okay, so this is the volume of cylinder outside the liquid, and if we differentiate this equation, then we can just replace Vi with V minus Vo. Okay, in this equation we already know that Vi into D is equal to M, and if we replace Vi with V minus Vo, so this is V minus Vo into D, it is equal to M, where M is the mass of the solid floating. So let us differentiate this equation. So dV minus dV naught into D plus d of d into V minus V naught, and that is equal to 0. Now if VO is constant, volume outside the liquid is constant, then d of V naught will be 0, and therefore d into dV will be equal to minus of dd into V minus V naught. Okay, and this is dV upon V minus V naught, and it is equal to minus of d by d. Now we know that the d rho by rho is the change in density upon original density, is minus gamma of liquid, obviously delta T or dt. So we can replace it with this one. So dV by V minus VO is equal to, this is minus of minus minus plus gamma dt, and dV is equal to V gamma of solid delta T. dV is the change in the total volume of the solid, and gamma of solid is equal to 3 alpha, because this is isotropic solid. So dV is equal to V into 3 alpha dt. and V minus VO is also equal to V immersed. So what we can do, we can write these, we can replace these values with this one. So V into 3 alpha dt divided by V immersed is equal to, this is gamma delta t, gamma dt, and cancelling this dt with dt, you can see that 3 alpha by gamma is equal to V immersed by V. Now we know that V immersed into D is equal to M. M is the mass of the solid. So mass of the solid can be written as density of the solid, which was, I think it was rho, and volume of the solid is V. So we know that Vi by V is equal to V by D. So we can replace 3 alpha by gamma is equal to Vi by V. Okay, so this is Vi by V, and Vi by V is V by D, where V is the volume of this. In fact, this is not V by D, it is rho by D, sorry. This is rho by D. So this is rho by D, and therefore the correct relation is this one. So you can see that gamma is 3 alpha D by rho. So gamma is 3 alpha D by rho. So you can see that this is the correct answer. So for option B, correct answer is R. Now in the third case, it is height of cylinder outside the liquid should remain constant. So height of the cylinder outside the liquid, we know that in the third case, C part, HO should remain constant. So we know that Vi into D is equal to M again, and Vi immersed volume is area, cross sectional area of solid into height of solid immersed into D is equal to M, and HO can be written as H minus Hi, where H is the total height of the cylinder. So A into H minus Hi into D is equal to M. Okay, so this is the equation, and what we can do, that A into H minus A into Hi is equal to M by D. And now we can, in fact, we can take just common, and this is H minus Hi is equal to M by D. Now we can differentiate this equation. So dA into H minus Hi and multiply by A into dH minus dHi. This is HO, in fact. Yes, because we have replaced this Hi with HO. So this is HO and this is also HO, and it is equal to, this is plus and it is equal to minus M upon D square into dd. Okay, now what we can do, that we know that dA is A into 2 alpha dt, because areal expansion coefficient of isotropic solid is 2 alpha, and d of HO is 0, and we know that dd by d is equal to minus of gamma dt. So we can replace these values and we can keep it here. So it would be d of a is a into 2 alpha del dt. So this is a into 2 alpha dt, and h minus ho is again hi. Okay, and this is a into d of h. Now d of h is equal to, we can write that d of h is equal to h alpha dt. So this is h alpha dt, and that is 0. dho is 0, which we have already discussed, because ho should remain constant. And this is equal to m by d into gamma delta t, gamma dt. Okay, so this is a into 2 alpha hi dt, and this is a into h alpha dt, and this is equal to m by d into gamma dt. Cancelling dt with dt, and you can see that ahi is vi, and again this a into h is v. This is 2 alpha plus this is v into alpha. Okay, and this is m into gamma by d. Now let us divide this complete equation with vi. So it would be 2 alpha plus v by vi alpha is equal to m gamma by dvi. Now we already know that vi into d is equal to m. So it is cancelled out, and this m is equal to volume of solid, complete volume, and density of solid, which is rho. So vi, yeah, or we can say v by vi is equal to d by rho. So we can substitute this value. So 2 alpha plus d by rho alpha is equal to gamma. So this is the correct required relation, and you can see that this one is this. So the correct answer for this option is S. And for D option, the height of the cylinder inside the liquid remain constant. So let us again analyze this case, D option. So HI remains constant. So again we know that VI into D is equal to M, and VI can be written as AHI into D is equal to M. So A into HI into D, in fact A into D, or we can write anything. This is A into D is equal to M by HI. Now we can differentiate this equation, and dA into D plus dd into A is equal to minus m by hi square into d of hi. Now d of hi should remain 0 because hi is constant, and therefore this is d of A into D plus d of D into A is equal to 0. So it means that dA by A is equal to minus of dd by D, and we know that dA is equal to A into 2 alpha dt. So dA by A is equal to 2 alpha dt, and we also know that dd upon D is equal to minus gamma dt. So let us write these values. So 2 alpha dt is equal to plus gamma dt, cancelling dt with dt. So gamma is equal to 2 alpha. So this is the correct relation for this case. So it is option number Q. So the correct answer for D is option Q. So this was the complete, I think it is the complete analysis of floating object and the effect of temperature on the buoyancy, the outer height, the inner height, the outer volume, and the inner volume. So that's why I was uh, calling this example as the complete perfect example for this concept. So this was it from my side, and let us conclude this video now. And we would be presenting more such topics and quality videos of the thermal expansion in the next upcoming videos. Thank you.